Good morning, everyone. Before we start, just for hygiene, I will request anyone has any question or clarification, they can put in the chat box and it will be responded within 24 hours, and then we'll take it from there. So, this session is the first of the IP TikTok series, which we have been thinking for quite some time, and then we have been able to work on this. The reason why we thought that this is important, it is primarily from the lot of discussions what we are having on green steel, and a lot of efforts are being done. How do we develop this? It's a very good initiative, and in last few decades, lot of work has happened. But the way we see, it's a long-term perspective, and it may take a few more years to make this commercially and technically both viable. Now, in the journey near net zero steel production, even though we are able to look for alternate technologies, but ISPs will have a role to play. And we also, from the Indian context, will have to see that how we can make it lowest producer of crude steel. At the same time, we move towards the benchmark CO2 footprint. And even though it looks contradictory, but in our view, both are possible. Where there is an opportunity seems to be of reduction of almost 1 ton of CO2 per ton of crude steel production. And this is based on average CO2 footprint data of the Indian ISPs. At the same time, we can also reduce cost of production by 5,000 rupees per ton of crude steel to 10,000 rupees, 10,000 ton per ton of crude steel, based on the specific condition of the ISP and at whatever stage they are in. Now, if we see from the impact, now if we are talking about 100 MTPA production crude steel through ISPs, then there is an opportunity of almost 100 million ton of CO2 reduction. And same time, when we add to the cost of production, then it can add a lot of investment opportunity to the ISPs, which can be also plowed in for development of green steel or others. So there, in fact, it is our privilege to have Mr. Girish Shetty. He doesn't need any introduction. He has more than 40 years experience in the area of energy, environment, sustainability. And we also realize that as a IP, we bring in operational experience. Our most of our experts have spent on the ground with the steel plant, whereas Terry brings in a lot of research, other perspective of technology, global perspective, and if we can combine this knowledge and experience, we believe that real impact can be made on the ground. So, with this, I will request Mr. Girish Shetty to share his thoughts and perspective and how to take this forward.
Thanks, Mr. Jha, I think, for the invitation. I think, let me first of all congratulate IP Tech Talk. I think you and, of course, Mr. D. N. Jha, I think, for taking this initiative of organizing this webinar today. And I think you plan to, as you were explaining earlier, you plan to have these as a weekly program over the next few weeks for the benefit of the people who are interested in the steel sector. So I think to me, it's really a honor for me to join this first session right at the start when you are planning to launch this whole program over the next few weeks. And of course, I have interacted with you earlier, and also with have heard that Mr. D.N. Jha is really the key stalwart who has worked for so many years in this field with the practical experience, practical tips, and I think what all we will be hearing from him over the next few weeks. I think if even part of that can be absorbed by the fraternity who is working in the real operation in the blast furnaces, in the steel plants, I think we'll be able to make much headway in terms of reducing the CO2 emissions. You talked about 100 million tons, but I think even a smaller percentage of that also, if we can get through these tech talks, people imbibe in their day-to-day operations, things can make a lot of difference. I think I would just like to, as you introduced me and you mentioned about TERI, but let me just say that as TERI, I think we are not really experts in the steel sector. We don't really, there's hardly one or two metallurgists in our team, but we are all people with energy and environment background. And when we are talking about carbon footprint reduction, which is a topic which you have selected for this whole seminar series, it's basically energy and environment. And we are all people who are working in the energy and environment field, and we work across sectors, we work across industry verticals, we work across maybe in the building sector, we work in the agriculture sector. Energy is used everywhere. It is so cross-cutting. But we understand CO2 emissions, we understand energy. And we believe that with this whole discussion globally, which is focusing quite a lot on the climate change issue, and TERI has been one of the pioneering voices from the developing world. Really, even when this Rio conference in 1992 was not, even before that, I would remember, when we organized the first international conference in TERI focusing on climate change. And then after the Rio conference in 1992, things started shaping up, and now everybody, the whole world really recognizes climate change as a real threat in terms of the global warming and how CO2 reductions have to be reduced in all sectors of the Indian economy. So from that angle, I think it's very timely and important that you have initiated this whole Tech Talk series on how we can reduce the carbon footprint from the steel sector. And if we really look at what we have been doing as TERI, I think in the steel sector, I can say that over the last 5-7 years, we have tried our best to really start focusing on the larger story of why the steel sector is so important and what have to be the broader pathways of how we can reduce the CO2 emissions from the sector. We have partnered in the last couple of years very closely with the Ministry of Steel in their efforts when they launched this whole report on the greening the steel sector in India. And in that, there were so many task forces, and one of the task forces, or rather two task forces, were very clearly focusing on the aspects of energy efficiency and CO2 reduction. And in fact, the third one was on RE. So to me, I think if one really looks at the overall decarbonization scenario for the industrial sector as a whole, I would think that there are 4 key pillars broadly, whether we are talking about steel or any other sector. The very first is, according to me, energy efficiency. I started my career with energy efficiency, and that still remains very close to my heart. So to me, energy efficiency is the very first step. In the short and the medium term, we must continue focusing on energy efficiency. And that is not just true for the large industries like the integrated steel plants, the BF route, which we are going to focus in this program today, but also for many other secondary steel industries, which are downstream operations, whether we are looking at the other route, which we are talking about, the coal DRI route, or even the downstream operations like the rolling mills, and everywhere I think efficiency will play an extremely important role. The second pillar, according to me, always in all these, when we are talking about is from the supply side, is the role of renewable energy. Wherever possible, of course, in the steel sector, majority of the consumption is in the form of coal. But in many sectors, or wherever there is a possibility, one has to move towards RE. And luckily in India and globally also, the cost for RE, whether it is the solar or wind, are coming down. And it is becoming very, very competitive with the coal-based thermal power plants. The third to me is a larger pillar, which is the whole story of circularity. How we can actually get moving towards using more and more circularity options in the processes. And in case of steel, I think to me the closest for that circularity word would be the use of scrap. How much ever we can use scrap, whether it is in we already are using. There are lots of smaller plants like the induction furnaces and others, and everything in the large furnaces, large plants also we are using quite a lot of scrap. But even in the other sectors, I think everywhere, I think circularity is an important. It is not just within the sector, cross sectoral also. Very clear example, I think, between steel and cement is that the better grass, the granulated blast furnace slag, which is a waste output kind of a thing from the steel industry, is actually becomes an input or a raw material for the cement sector. And that's how we get the Portland slag cement. And in fact, many plants have actually come up around the. I remember earlier, I think even the Tatas, in fact, have been started long back, I think, and even JSW cement also. So they are using slag as an important thing, which goes to make that. So circularity as a whole is extremely important when we're looking at reduction in the carbon footprint. And finally, I think whatever cannot be reduced through these three first levers, which are the short-term levers, will have to be moved towards when they're looking at a net zero kind of a pathway. We'll have to move towards those options which have yet to become commercially viable. Things like the hydrogen DRI we are talking in the steel sector, or in other sectors we are talking about electrolysis, or maybe carbon capture storage, or any new technology which are yet to come to the horizon. So to me, I think in the short to medium term, I think one will have to continue focusing on these kind of aspects. And within that, I think the whole story of how the optimization have to happen, how digitization and process control, real-time energy monitoring, these kind of things, how they can actually help reduce the uh, requirements of energy within the operations. And these are all, I think, cost-effective, technically mature ways to really move forward. And there are so many other best available technologies, I think, which I guess will perhaps get featured, things like the CDQs and the TRTs and the waste heat recovery systems within the plants. I think all those would really get, I don't want to get into that because that is for somebody like Mr. Jha and you to really take it further. But to me, in short, I can just simply say at the start that I think the decarbonization of the steel sector, I think, will have to have a dual track. The first one will, of course, have to be in terms of accelerating how we can increase the efficiency and resource efficiency measures in the short to medium term. And in parallel, the second track will have to be how we can actually start looking slowly, or in terms of the newer technologies which are on the horizon. We have one sees, I think, things happening in some parts of the world, in Europe or elsewhere, but one will have to look at those longer term options. But these are the dual tracks we'll have to focus. And with these few words, I think I'll stop here and I'll give it back to you, Mr. Jha, for the further deliberations today.
So very much, Gireji. I think you have your articulation is absolutely bang on when you talked about dual track, and that's the core of our success, where we have to work on both short term and long term together, and we should build on that. With this, I would like to invite Mr. D.N. Jha, who has again more than 40 years experience across this field, and primarily on iron making. And he is the person who basically not only build phase one of Kalinga Nagar complete iron making, but in his role as general manager engineering for the Tata Steel Group, he has worked not only for Tata Steel Indian steel plant, but also he has worked on the master plan for Tata Steel Europe entity, and he understands what is the how we can achieve whatever we are talking about. So with this, I will request Mr. D.N. Jha to initiate this series of TikTok and wish him all the best. Jha sir.
Thank you very much. This subject is very close to my heart because of the impact that it has got on the humanity, apart from the impact that it has got on the economics. If we look at the Indian scenario, then you will find that gradually the output from Europe, output from North America, and output from the other developed countries is shrinking because of the impact that it has got on the climate change. Now, if we look at the other countries, then today the China is contributing to roughly 60% of the steel output. And India is the second largest producer of iron and steel. So as we look into the future, the portion of the Indian output is only going to go up. That gives us an opportunity of expanding not only economically, but also puts us a great burden in terms of the contribution towards the climate change, towards the CO2 emission, adding to the CO emission. So unless and until we wake up and as a responsible country towards the climate change, unless until we make very mega steps, it will be very difficult in terms of the climate worldwide. And it is our duty to cater to the humanity, not only to the present generation, it is going to affect the future generation. And therefore, if we look into the future, almost in the immediate future, our country has set up a target of roughly producing 300 million tons by 2030, which is not very far away. It is only 5 years from now. Now, if we look at the present scenario, then our emission of from the steel plants that we operate within India, it is 2.55 million tons of CO2 per ton of crude steel. Let me explain that when we say that why we say per ton of crude steel, because this is important. Because you will find that different steel plants have got different outputs. And somebody is making longs, somebody is making flats, somebody is casting, somebody is not casting. So those finished products are different, and therefore it may be very difficult to compare one plant with another. However, every plant is going through the route of crude steel. So if we look at the CO2 emission or the energy or any other parameter, then if we look at per ton of crude steel, it equates. So everybody is normalized. And then we can compare what is the emission, CO2 emission from one plant versus the benchmark plant. So it helps us in seeking the direction in which we should be proceeding. Second aspect is that that of economics, because we are in the industry, and every venture is a techno-commercial venture. So if something is technically viable, then it also needs to be commercially viable. Because if it is not commercially viable, then in the long run, we cannot sustain. So we need to look at the things in the longer run. Because all the steel plants, they have a gestation period and they have a life. And that life is pretty long. So if we invest something, then even in the iron making, roughly the life that is assumed is going to be 15 to 20 years. The modern iron making units, they last for roughly 20 years or thereabouts. So if you have invested, then you are looking for the returns for at least 20 years. So Therefore, our vision must look at the things which are cost effective, because it's a commercial venture. It should be cost effective for at least 20 years. So, second, now if we look at the Indian scenario, then there are certain things that we must be aware. One is that there is a dearth of natural gas. So, natural gas, which is available at for some countries, that is not available in India. However, the India has got ore, iron ore, albeit not of the best quality. The quality of the iron ore is not standard, it is a kind of substandard. It has got certain limitations. However, there is plenty of iron ore which is available in India. So we talked about first the opportunity that the country needs to expand in terms of iron making. That's an opportunity. There is another strength that we have ore and ore within the country. So that is another strength. But if we look at the coking coal, then we are short in terms of coking coal. So we need to import. Now, coke or coal has, why talked about this, is because that is the major source of energy and major source of reducing agent in the iron making unit, or the integrated steel plant. That's the major source of energy, major source of reduction process. And therefore, now the kind of the carbon units or the coal that we need, there is a dearth of that within the country, and therefore maximum amount of coking coal, nearly 90% of that, is imported from different parts of the world, majorly from Australia, but there are other countries also where from it is imported. Now, if we look at our emission, then as I said earlier, it is including all the technology used in the integrated steel plant. It is around 2.55 tons per ton of crude steel. Whereas what we're going to see in the subsequent sessions, that we can bring it down to 1.6 ton per ton of crude steel. So therefore, there is a gap of nearly 1 ton of CO2 per ton of crude steel. So as we are expanding in capacity, and if we want to remain in terms of emission at the current level, then there is an opportunity and of reducing the CO2 without, let's say, impacting the climate or greenhouse gas emission. So this is an opportunity, and therefore we must utilize this opportunity. Second aspect of that is, since major amount of this is coming from the carbon, which is an energy agent and also reducing agent. So if we reduce that, then it has got tremendous impact on the cost of the steel making. Today we are struggling to keep ourselves floating because Chinese companies, they dump their material in the world, and they are going to be in future also, they are going to be a very substantial force to reckon with, and their cost of production is lower, and therefore we have to compete in the international scenario in terms of cost. And so it gives us an opportunity of reducing the CO2. First of all, we need to understand where the carbon is, where carbon is being utilized, and what can be done about it. So as I said some time back, that carbon is utilized in terms of producing heat and also in terms of reduction. Now, if we are looking at the use of the carbon, then the carbon is coming in the iron making unit in the integrated steel plant. Major amount of carbon source is through the coke. Now, if we look at how much carbon is coming from the coke, then let's say the coke is being made through the coking coal. So coking coal is, there is a dearth of coking coal, and which we are importing from Australia or any other country, which has got certain properties. So for coking coal, there are certain characteristics which need to be there. And one of them is that it needs to be low ash and low volatile material. If because if we have a higher amount of ash, then it contributes to the slag, and which again demands more energy. So therefore, we need to have lower ash, and that is what people buy. Now, we need to again look at this scenario of the property of the coke or property of coal when we are buying, and we need to look at the cost effectiveness of that versus the properties that we are looking at. So if I am enhancing certain property, that is coming at a cost. Also, it is contributing to the CO2. So we need to look at both of these and try and optimize it. So the decision matrix need to look these two factors into consideration, and then we need to look at the decision making matrix. That's one. The second part, so the now the carbon is, if we look at the iron making, then there are two things which are happening. One is the reduction of the iron ore, reduction of Fe2O3. If we look at the iron ore itself, then iron ore, we have plenty of iron ore within the country, and which we may not import in the near future or in the midterm. We don't need to import. However, the amount of the beneficiation that needs to be done, it has to be justified by the techno-economics of it. Because if we beneficiate more, then it has got certain impact on the yield. Now, so however, if the advantage of losing the yield versus the advantage that we have in terms of the cost or in terms of the CO2 emission, then we can look at the scenario. So there will be a decision matrix, and therefore we can look at that. I hope I am able to clarify till now.
Yes, I just wanted to understand
Yeah.
the role of coking coal,
Yeah.
and when it gets converted to coke
Mhm.
for in the blast furnace. Is it only when you are talking about, is it only for providing this energy or reducing agency, or it has got something else also?
No,
Why
it
do
has,
we need coal? Coke. Yeah.
we need coke for various reasons. One is that coke is the only solid material which remains in solid form till the in the blast furnace, because in the blast furnace we encounter a temperature which is up to a max of 2300 or 2400. Coke does not let's say liquefy till that temperature, so it remains in the solid form, and it also has got certain strength. So the burden that it is supporting, it is the support function, because being in the solid form, it can support certain weight. And so burden column weight is supported by the coke. And this is second thing, that it should not get, let's say, oxidized very much. So that by the time it reaches a place where the temperature is high, it should the size of that should not be such that it crumbles into fines. And the third part is that it should the size of that should not be so low that it packs the heart, packs the bottommost portion of the blast furnace, because let's say the liquid hot metal has to pass through that. So these are at least some functions which demand certain properties of the coke, which is known as CSR and CRI, coke strength after reduction, and coke reactivity index. So while the reactivity should be low, the coke strength after reduction should be high, such that the size of the coke in this zone still is high, and still it has got the strength to support the column weight of the burden. Have I
Okay.
clarified?
Yeah. So whatever I have able to understand from your explanation, it means that theoretically it may not be feasible to replace coke with hydrogen or any other gaseous fuel in a blast furnace route of iron making.
Yeah, you see, in the iron making, there are, if we look at, there are two distinct phenomena which are happening. One is the reduction process itself, okay, and the second is the heating process, such that we get a molten metal. Oh, okay, so we need heat, and at the same time we need the reducing gas. So if we need the reducing gas, then hydrogen can substitute. Also, the hydrogen can give heat, but what it cannot do is supporting the column weight, and what it cannot do is also, let us say, creating a void in the hearth such that the hot metal can pass through and we can tap the metal. So there is a difference, and therefore there is a certain amount of coke which remains in the solid form and beyond a certain size, such that there is a void, and the hot metal can pass through. That gives a limit to which we can go in terms of reducing the coke rate.
Okay. Thank you. Please go ahead.
Right. So now, if we look at the single most expensive material in the iron making, or even up to the steel making, the single most expensive material, that is the coke. So if we have to reduce the CO2, as well as if we have to reduce the cost of the hot metal, then we must attack the coke. And as we discussed a couple of minutes back, we need to reduce the coke to the minimum possible. And minimum possible is what? There are two things which cannot be substituted by any other material. One is that column weight it must support. Second is that it must remain big enough size such that the hot metal can pass through it. Means the permeability of the hearth should be such that hot metal can pass through and we can tap the hot metal through the tap hole. So these are the two phenomena which decide the minimum amount of coke. And here we are not talking about the heat, here we are not talking about the reduction process, but just the phenomenon of production of the supporting the column weight and passes of the liquid. So these are the two things. Now, if we look at the iron making unit through the BF route, then we have, apart from this, there are two things which are very distinct. I'm oversimplifying the process, but to make it understandable, there are two phenomena which are happening. One is the reduction, and second is the heat generation. Why do we need reduction? Because So, ore we charge in the iron making unit, we are charging sized ore, sinter, and pellet as a Fe source of, let's say, Fe source for the hot metal. Because we what if we look at the sinter, then sinter also has got Fe2O3, but there is a small amount of FeO, something like say 9 or 10%, up to a max of 10%. That is the FeO, but rest of the material is Fe2O3. Similarly, the pellet has got maximum amount is Fe2O3. If we are charging sized ore, then that is also Fe2O3. So Fe2O3 needs to be reduced to Fe. So this is one process that where we need some reducing gas. Also, so reduction is one process for which we need reducing gas. There can be, when we talk about the reducing gas, then the reducing gas can be CO and can be hydrogen. However, if you look at the CO, then the CO generates in let's say when it is getting oxidized and is becoming CO2, then it is producing, let's say, 3014 kilocalorie per meter cube. Just remember this number. Let's say a little more than 3000. Whereas if we look at the hydrogen, then hydrogen is generating, let's say, heat, which is 2570 per cubic meter. So there is a difference in the heating value in when it is getting oxidized. So if we in short, if we look at the difference between these two, the difference is roughly 430 odd kilocalorie per cubic meter. So you understood that if we are using hydrogen, then we are not generating enough heat. This is during the oxidation process. So if we are not producing more heat, then we need to provide heat through some means. It could be through more hydrogen, or it could be through more CO. Okay, is this making sense?
Yes, yes, I
Right,
think this is clear.
right. So if so hydrogen, if we are using, then we would need more amount of hydrogen for generating the same heat, because for the reduction process it may remain the same, but for producing the heat, because all the reduction that is happening, it cannot happen at the room temperature, because since it cannot happen at the room temperature, so we need to heat it, need to heat at a temperature which is close to 900 or plus. And since this heat needs to be produced, so therefore we would need to oxidize let's say the hydrogen, or we need to use carbon monoxide. Now, if we look at the carbon monoxide, then in the blast furnace, or in the iron making route that we are talking about, the classic route, then the carbon is first getting oxidized to carbon monoxide. So once it is oxidized to carbon monoxide, then it is generating something like 2450 kilocalorie per kg of coke. So this is per kg of carbon. So this is small amount in comparison to the total oxidation. However, this CO is going to above and is going to reduce the Fe2O3. And once it is reducing there, so first it has generated heat here at the bottom of 2450. If we are substituting this amount by hydrogen, then at the lower portion, it is not generating any heat. Unlike the CO, where it generated 2,450 kilocalories at the bottom, and which is sufficient to keep it molten. This is a big source of energy. And above, then it is when it is doing the reduction, there also it is generating some amount of heat, which is 3014 kilocalorie per cubic meter of CO. In comparison, if we are using hydrogen, then in the bottom portion where it needs to keep it in the liquid form, it is not imparting any energy. And therefore, if let us say this is the heating is a bottleneck, then we would need more amount of carbonaceous material, because even if the hydrogen is sufficient to reduce, we need some amount of carbon to keep it in the fluid form. So is there any question till now?
No, I think maybe as you move further, I may have
Yeah.
some
Okay.
clarification, but this is
Fine.
perfectly okay.
Right. So this is a kind of the broad understanding why we cannot use all hydrogen if we are going through this route. Now, in this route, if there are certain things which we need to establish and then we need to provide for. So, first is that we need to look at the scenario of the integrated steel plant, and we need to optimize on the slag. Slag is something because we have ore, okay, Indian iron ore. Now, primarily, we what we are looking from the ore is Fe, okay. But you will find that there is no ore which has only Fe or Fe2 or 3. It also has got some impurities which are known as gangue material. So gangue material would be in terms of let's say in the form of alumina, Al2O3, silica, which is SiO2, plus there would be a small amount of phos, there would be a small amount of titania, and small amount of other material. So the primary gangue materials are in terms of alumina and silica. So if the gangue material is small, then the amount of slag which is containing the gangue material as an undesired, or let's say the purification mechanism, then the slag can be lower. However, if the gangue material or the impurity is higher, then the slag also will become higher. And if the slag is higher, then that would call for more heat and therefore more energy. So it is better. However, the economics demands that if we have to use more of Indian iron ore, and we do not, uh, we want to use it to the maximum, then in that case, the slag can become higher. Now, the slag is also determined by what is the ratio of the burden. That means, say what is the percentage of pellet, what is the chemistry of the pellet, what is the percentage of sinter, and the chemistry of sinter, and the iron ore. What we look for in the iron making units, that there is a particular way in which you design the burden. And when we say designing the burden, then it talks about the percentage of each one of them and the chemistry of each element. Chemistry means we can hardly change any chemistry as far as sized ore is concerned, but we can definitely change the chemistry of the pellet. We can look at the chemistry of the sinter. So now if we change, or these are, because sinter and pellet are synthetic material, so and we can change the chemistry of this. And depending upon the chemistry and how we have determined the chemistry of this, the slag rate is going to be determined by that. Also, the chemistry affects the reduction properties. So if we have to, let us say, improve the CO2 emission, then the reduction process needs to be improved. And if reduction process is improved, then the reducing gases can come down. And if the reducing gases can come down, then it affects the CO2 process, okay, CO2 emission. Now, if we look at, let's say, in the broader terms, today I'm not getting into the detail of any one of these, but in broader terms, I'm trying to explain. So, if we look at the carbon that is coming out from the blast furnace, where is it going? Because we are charging carbon into the blast furnace from the coke, we are charging also from the coal injection. These are the two sources through which we charge the carbon into the blast furnace. But where is it going? The carbon is going somewhere. So carbon is going in the hot metal, roughly 4.5% of the hot metal is carbon, because this carbon gets dissolved in the solution of hot metal. So because at that temperature, carbon is soluble in the hot metal. If it's a small blast furnace, then you will find that the carbon is around 4%. If it is a bigger blast furnace, you will find that the carbon is nearly 4.5 to 4.6%. This is roughly the number that we have. So if we say 4.5%, that means we are talking about 45 kg of the carbon is going in the hot metal itself. The second portion of the, or rest of the carbon, where is it going? Rest of the carbon is getting let's say the gasified, and once it gets gasified, then it comes out through the top gas, through the blast furnace top. There is a gas which is coming out, and that gas contains the carbon is in form of carbon monoxide and carbon dioxide. Okay. Now, since it is carbon having carbon monoxide, it has got calorific value, and we should tap the calorific value, utilize it to the maximum, and we should not waste the carbon monoxide from there because it has got heat value. So there are only two places where the carbon is getting out. Now, that is not, the gaseous carbon is not fully utilized in the blast furnace. That is utilized in the rest of the plant. And if we are balancing very well in the plant, then we would be using all forms of energy requirement in the steel plant, in an integrated steel plant. We should be able to use all the byproduct gases to the maximum, and we should not be requiring any energy from outside. This is a big statement that I have made. If we are having, let's say, utilizing all the byproduct gases, then we should not be needing any form of energy from anywhere else. Okay. Yeah, that is it.
Yeah. So, are you saying that if we are energy efficient
Hmm.
to the benchmark level,
Yeah.
then we don't need any external power or energy source in addition to whatever coal we are using in terms of coke or PCI injection in the blast furnace?
Yes, that is what I said. However, we need to be connected to the grid for startup loads and things like
No, that is okay. I mean, connection of the grid is one
that.
part,
But
but
as far as energy requirement,
100% of the energy requirement
yeah,
till up to crude steel production can
yeah,
be met by whatever coal we are using through coke or PCI.
yeah, correct, correct. So, and also when we are producing coke, then that is produced through the coke ovens. So coke ovens is also generating some byproduct gas, which is known as coke oven gas. So coke oven gas plus the blast furnace gas and plus the LD gas, these three taken together, the total amount of byproduct that we are generating, if we are utilizing it, then we should not be needing any energy from any external source. So, is that clear? I think,
Yeah, I think Pranesh has some
yeah.
observation.
Uh,
Yeah, Pranesh?
Good afternoon, sir.
Good afternoon.
Actually, I am new to integrated steel plant. I
Okay.
am having only the experience of pelletization and the beneficiation till now.
Okay.
So I heard, I just during this, you were explaining that we are able to produce 1 ton of hot metal by 2.55 ton of crude steel. So I was just thinking that why it is so.
No,
So it
no,
is so
what I
high.
said,
Yeah.
sorry, what I said that if you produce 1 ton of crude steel, then we are generating in India, the average generation of CO2 is 2.55
Okay.
tons per ton of crude steel.
Understood, sir. Understood. Thank you. I will correct my mistake. Thank you.
Now, this is where what I said that since this figure is high, 2.55 is very high. So as we have planned to increase the production of steel within India, therefore the CO2 also is likely to go up. Now we need to take measures such that the CO2 emission from the Indian steel plant remains capped at this value or comes down. And that is what we are going to talk in subsequent weeks. We're going to talk about this. Some part I am trying to explain how the CO is generated or CO2 is generated in an integrated steel plant. And where is it being used? Let's say. So, till now, I have not given any quantified terms, but we can do that in the subsequent lectures. Yeah, Rajesh.
Yeah, so one thing what you explained clearly about the carbon portion in the gaseous, whatever
Right.
coming out, it is CO or CO2.
Yes.
But as per my understanding, it is coming out at certain temperature, so it also has a sensible heat.
Correct.
So,
Correct.
so how are we going to deal with that if we are talking about, if we are thinking about energy efficient plant?
Right. Right. So, as we will get into the detail of that, since the top gas is at a certain value, which is higher than the ambient temperature, therefore the enthalpy of that gas is higher than what it would be having at the room temperature or at the ambient temperature. Typically, the top gas temperature varies between 100 degrees to 140 degrees, depending upon plant to plant basis or depending upon the operating parameters or depending upon the operating skills. This varies from 100 degrees to 140 degrees. Now, since this is the ambient temperature being, let us say, 35 or 40 degrees, if it is higher by certain amount, then the enthalpy of that top gas is higher. And since the enthalpy is in the top gas is higher, so we can harness or we can, let's say, generate more energy through that, and we can recover more energy through that if we do not kill the temperature. See, traditionally you will find that in the blast furnace, this top gas temperature, the top gas is washed, it is washed to bring down the dust content. Now, if you use the normal scrubber for washing it, then the top gas temperature is also coming down to 40 degrees Celsius. But if we are bringing it down from 140 degrees to 40 degrees, then we are losing this enthalpy. And if we are losing this enthalpy, then the amount of energy that we would be recovering would be lower. See, if we talk about the total energy, then we have three forms of energy. One is the pressure energy, the second one is the potential energy, and the third is the kinetic energy. And this will remain constant. So if we are recovering, let's say, the pressure energy through the TRT, top gas recovery turbine, and if enthalpy is lower, then the pressure energy that would be converted into the kinetic energy and then to the electrical energy through the top gas generator, that would be lower than if we are not, let's say, losing the temperature. So we will talk about the details of that technology, how we can clean the gas without losing the temperature. Okay, and therefore we can recover more energy from the top gas. That we would be covering in the subsequent sessions, detail of that. But just in terms of hint, I've told you that this is what we should be doing if we want to conserve the energy. Any other question?
No, this is okay. So maybe we are also nearing to the end. So maybe in next few minutes, you may like to summarize whatever you have covered and what you would wrap up in next session.
Right. So in a couple of minutes, I would try to summarize. First is that India has got great responsibility and a great opportunity of expanding in terms of the manufacturing of iron and steel. Because as previous decades that if we look at, then China took this opportunity of expanding and they have flooded the market with their product. Now they have saturated, so as the developing countries demands would increase, India is in a better position to expand. And India, for that, India has got not only the opportunity, it has got the strength of having the iron ore within the country. And now the second challenge is that when we are trying to expand, then we should not be adding to the CO2 load. So we, as a responsible country or responsible global citizen, we should be curtailing that CO2 emission so that we do not contribute negatively to the climate. And the third aspect is that as we are doing that, then it should be cost effective. So as a matter of fact, if we follow all the things, then we would be talking about the steps through which we reduce, we keep the CO2 same, improve the productivity, bring down the cost, and for that, what are the measures or what are the levers, we'll be talking in the detailed sessions subsequently. This is what we have covered till now in brief.
Okay, and what you plan to cover in the next session?
In the next session, we would be looking at the detail of where carbon is used within an integrated steel plant and what is the theoretical minimum that we can achieve, and such that we know at a potential of what we can do. Because for finding out the potential, one is that you look at the benchmarks. Also, we need to look at, as we are the second largest producer of iron and steel within the world. China is the first. Then we may not depend on only the world benchmark. We also need to have the theoretical insights into what is possible, what is not possible. That is why it is this is the going into the direction as a corporate, as a a responsible corporate country.
Thank you. So see you then next Thursday, 12 noon.
Yeah.
Thank you. Thank you all.